In today's lecture, I want to talk about the DTFT of periodic signals. The learning objective of this lecture is to describe and characterize the DTFT of periodic signals and to do a couple of examples. The main takeaway message of today's lecture is that the DTFT of periodic signals can be defined, and it looks like an impulse train in the frequency domain. So it looks something like this. So if this is the frequency domain, then the DTFT, let's suppose this is 0 here. So this is x of e j omega. So it may look something like this. So let's suppose you have these pulses here, and we know that the DTFT is periodic with period 2 pi. So if this is for example plus pi, and this is negative pi, and so on and so forth, so what you would have this pulse repeated. So you would have also the same shape here, repeated here and repeated here, so every 2 pi, and also here. So it looks like an impulse train. And I want to describe this in more details in the next few slides. Let us start with an example. So let's suppose we are interested in finding the DTFT of a complex exponential signal, which looks something like this here. So x of n is e j omega 0 n, and this is e j omega 0 n is at least in the continuous domain, is a periodic signal. Now, if you think of it for a second, you can see that this signal is periodic and has frequency omega 0. So, in some sense, in the frequency domain, it should have a frequency at omega equal to omega 0. So, if I want to draw this, so let's suppose in the frequency domain, so this is x of e j omega, you should have frequency at omega 0 here. So this is the omega axis. So you should have a frequency here. It's 1 here because the coefficient is 1 here. If you had coefficient 10, that would be 10 here. Right, so this is intuitively what should be there. But we know that x e j omega is periodic, so actually what we have a repetition. So this is true, so we'll have one impulse at the frequency omega equal to omega 0 in the interval minus pi plus pi, and this impulse is replicated. So this is 2 pi plus omega 0, and then 4 pi plus omega 0, and so on and so forth. So here you would have also the train of impulses. So that's what I want to show, that the DTFT of a complex exponential signal, which is e j omega 0 n, is a train of impulses at frequencies at frequencies that are omega plus multiples of 2 pi. So here I have again the result that I mentioned, which is that the DTFT of a complex exponential. Now if you want to write it in a formula, you will get the following formula for the DTFT of an impulse at omega equal omega 0. So you can see here that you have a train of impulses, and that are spaced by multiples of 2 pi here. So here is the sum from L equal to minus infinity to plus infinity, 2 pi delta omega minus omega 0 minus 2 pi L. Now I can see here already a typo, so here it's 2 pi. So let me fix that. So here it's 2 pi, it's not pi. Now, if you just wanted to understand the relationship between how this formula gives you this graph, so for L equal to 0, you get omega minus omega 0, so you have an impulse at omega 0. For L equal to 1, you get omega minus omega 0, so maybe if I do it on the side. So for L equal to 1, you get an impulse at omega minus omega 0 minus 2 pi, which means the impulse is at omega equal to omega 2 pi minus omega 0. So 2 pi plus omega 0. So you get this impulse here. So each L is just going over these impulses, with L equal to 0 is here. And this is an important formula that I would advise you to kind of memorize it, because it's going to be helpful later on. Now, why this formula is correct? Now, if you look at the signal x of n, which is ej omega 0 n. Now, if you try to do it the regular way, by regular way I mean by applying the formula, so you're gonna get that x of ej omega equal to sum from n equal minus infinity to plus infinity of well, you're gonna get here ej omega 0 n e minus j omega n. So you're gonna get the sum of e j r minus j omega minus omega 0 n. And now you would think that this is a geometric series. However, this guy here, the norm of this guy is equal to 1. So it's not clear that this is going to converge. So I cannot apply the geometric series here. So we're going to prove this formula using a different way. And the way we want to do is actually just verifying that this is the correct DTFT. And we do this by just finding the inverse of it and showing that the inverse of it is actually the impulse response. So we start by the given that the DTFT of a signal is the following. This one here. So this is x of ej omega. And the question is to find x of n. And to do this, we apply the inverse DTFT. So we know that x of n is the integral from negative pi to plus pi of 1 over 2 pi, the sum of L equal to minus infinity to plus infinity 2 pi delta omega minus omega 0 minus 2 pi L ej omega n. So here, this is going to pull up the nth component of the signal, d omega. Again, I'm just applying the inverse DTFT formula. Now you have to be careful here. It's just the rest is just calculations. So you can bring the integral inside the summation, and you can simplify by the 2 pi here. So you get the sum from L equal to minus infinity to plus infinity, the integral of this whole thing here. And recall that here you're integrating over the interval minus pi plus 2 pi. And remember, this guy here is the following impulse train. So it looks something like this. So if I want to draw it in blue here. So this is your delta. So this is minus pi plus pi. So you have somewhere here omega 0 and somewhere here. But you're only integrating in this space here, so you're only doing your integral in this space here. Sorry, here. Here. In this interval, minus pi and plus pi. So you're only going to pick up this impulse, and the rest are going to be 0. So this is why this is, out of all this summation here, the only thing that's going to matter is L equal to 0. Or this summation here. Right? Because this is the only impulse in these boundaries. So, and for L equal to 0, what I get is, I get Ej omega 0 n times delta omega minus omega 0 d omega. And this will give me Ej omega 0 n at the end. So what I pick, so x of n is exactly the one, it's a complex exponential that I started with, so, which means that the formula is correct. So it is important to remember in this case that the DTFT of x of n equal to Ej omega 0 n is actually the train function x Ej omega 2 pi, the sum of the impulses. Right, so this is something you have to know. Now we get to another question here, which is to find the DTFT of the cosine function. Now you know by Euler's formula is that the cosine function can be written as a sum of two complex exponentials. So I can do what I can do here is I can write this guy here as 1 over 2 Ej omega 0 n plus E minus j omega 0 n, and then I can, by linearity, I know that I will have the DTFT of the cosine is going to be the DTFT of this part plus the DTFT of this part, and you have 1/2. So the 1/2 here is going to kill the 2 factor here, so you get the pi outside, and then you have the sum of the exponential of the impulse responses. So you have 2 sums here. So the first sum is the Ej omega 0 sum. So maybe let me color it or highlight it in yellow. So this part here corresponding to Ej omega 0 n, which is the one we just did. So it's going to give you these pulses at omega 0. Also here should be omega 0. That's a typo, I will fix it later. And the other part here in green, if you take L equal to L0 here, so for L equal to L0, you're going to get delta omega so here it should actually, there's another typo here, so here it should be plus omega 0. So this is gonna be delta omega plus omega 0. This means you have an impulse at omega equal negative omega 0, and this will give you these impulses here. And you can see how, again, you see the main message of this lecture is that the periodic signal, the DTFT of periodic signal, is a train of impulses. Now the DTFT of the sine function, again, it's the same way. I'm going to do it really fast here. So we know that the sine function is 1 over 2j Ej omega 0 n minus E minus j omega 0 n. And this is why you're going to get pi over j here, so this j here, and then you have delta omega minus omega 0 minus 2 pi L and omega plus omega 0 minus 2 pi L. So this part here is going to give you the frequencies at omega 0 and its shifted versions. And this guy here is going to give you the frequencies at negative omega 0 and its shifted versions. So this is by the way, so this is an exponential function. So usually this is more like a representation of the graph, because now x of e.g. omega is exponential, so it's not real. So what we usually do, but I mean this is more like a conceptual graph here, because I have minus pi by j. This is obviously, if this is the y-axis, I mean these two axes here, I assume that the signal is real, but this is just to tell you how the signal looks like. So, but if x of ej omega is a complex, meaning it has a non-zero imaginary, then we usually have to have two drawings, one for the amplitude of x of ej omega, and one for the angle. So if you want to call it theta of ej omega. And at the end of this lecture, I have a do-it-yourself exercise, and the exercise is that to show that the DTFT of a periodic impulse train in time is a periodic impulse train in frequency of the same form. So, and first, the first statement follows immediately from what we did, because an impulse train in time is periodic, and therefore the DTFT of it is also an impulse train. And now the question is, how does it look like? So the impulse train in the time domain looks something like this, and I want you to show that this would be the DTFT of it. So please show. You need to show this thing here. That it's a series of impulses separated by 2 pi k by n. So if in the time domain you have impulses every n steps, so here you can see, so you have an impulse at n equal to multiple of n. So you have at 0, you have at n, you have at 2n. So you have impulse here, and impulse here, and impulse here. And the guy here is going to be, the xej omega is going to be impulses, but so here it's 1, but they are separated. So so it's going to be at 0, and you have at, so for k equal to 1 at 2 pi by n, 4 pi by n, and so on and so forth. And also in the negative, so you're going to get something like this. And the amplitude here is 2 pi by n. So that's basically what you have to show.